So could you please tell us about who you are?
Hi, my name is Jack Langelaan, and I'm a professor of aerospace engineering at Penn State University. And I've been at Penn State since 2006. I did my PhD at Stanford, and I worked as an engineer for 5 years at Bombardier Aerospace in Toronto, Ontario.
Mhm. And why did you want to become an aerospace engineer?
I've always just loved airplanes. Ever since I was about 3 years old or so. So my father, his hobby was, as a hobby, was a glider pilot. And so he would bring me to the glider field all the time. And I've just loved airplanes ever since I was about 3 years old. And so I've always known I want to do something with airplanes. If I had perfect vision, then I would have tried to be a pilot in the Air Force, but I don't. I have Coke bottle thickness glasses. And so the next best thing for me was to go and work on aircraft design.
Mhm. So your primary research areas are related to autonomous vehicles and vehicle dynamics and controls. So can you explain some of your work in vehicle dynamics and controls?
Sure. So most of the stuff that I do has to do kind of with what we call guidance and flight planning and navigation. And they all kind of work sort of at different levels. One of the sort of definitions of all these things, right, between control and guidance and navigation says that navigation is the sort of field of figuring out where you are and figuring out the path of how you want to get to from where you are to where you need to go. Right. So navigation is where are you and how do you get to your destination? Guidance is the field of figuring out what should your flight condition be so that you follow that path to your destination. And control is what do you make the airplane do so that you follow those guidance commands of, for example, an airspeed and the desired heading or whatever, right? So the control side of things is really stuff that occurs on board the airplane at fairly high rate, right? It's the deflection of control surfaces, it's the management of the throttle of the engine, right, or of the aircraft, and even on a lower level, management of all the little things that happen inside the engine to make sure that the right things are happening. So my work focuses more on the guidance and on the navigation side, which is figuring out how do you get to where you want to go, and how do you decide what you want the vehicle to do in order to do those things. And the parts that we work on are things like how do you get a small unmanned aircraft, a little UAV, to fly from its destination or from where it is to its destination using minimal total energy, right? And so we do things like exploit winds in the atmosphere to help us along the way, doing things like, looking for regions where the wind is in a favorable direction, avoiding regions where the wind is not favorable. We'll do things like if we're flying along and we detect a region where there's upwards motion in the air, something we call a thermal, right? And if you've watched turkey vultures and eagles and hawks, or if you're a glider pilot yourself, right, they always do this: is that you find a patch of warm air and you fly in a circle in a patch of rain, you gain altitude. And so we can set up our aircraft flight control systems to be able to exploit those things, right? And so it's sort of minimum energy flight planning for the aircraft. One of the other things that we've been doing is trying to get a group of small multi-rotors to cooperatively carry a payload. So we've got 4 little multi-rotors, all of them connected to really for us, it was a beer cooler. And they cooperatively carry this thing. And the problem here is how do you control the vehicle so that they can work together to carry this heavy payload? And kind of our sort of fun, really exciting project right now is NASA's project called Dragonfly. And Dragonfly is to send a drone to Saturn's moon Titan. It's sort of managed and run out of Johns Hopkins Applied Physics Lab. And at Penn State, we're working on the, what we call the rotorcraft side of things, right? And basically a lot of the stuff to do with the drone itself. And there, what we're doing is working on aerodynamic design of the vehicle. We're working on flight performance of this thing. So Titan is a neat place to fly because its gravity is quite low compared to Earth. It's 1/7 of Earth gravity. and its atmosphere is very dense. And so that combination means that you can fly a pretty large vehicle on Titan for significantly less power than you would need to fly that same vehicle here on Earth, which means it's now, significantly more, easy, in some respects, significantly easier to fly a vehicle on Titan than really anywhere else in the solar system, right? We're flying the Mars rotorcraft on Mars. Mars has fairly low gravity, but its atmospheric density is also very low. So flying on Mars is actually very difficult and challenging. And what the Mars helicopter team has done is really impressive and really cool. So our sort of coolest thing right now is the Titan drone. And we're all of us really excited about that.
And what are some of the upgrades that you're researching in autonomous vehicles?
So I see my work as focusing on a couple of different things. One of them is an area that I call persistence, right? So how do you get an unmanned vehicle to spend a long time in a spot, right? And so we do that by doing this work on autonomous soaring flight, finding favorable parts of the atmosphere to fly in. And by doing that, we can improve the endurance of a small aircraft by several hours. And we can improve the distance that it can fly by a huge amount as well, right? So that's kind of our first P is persistence. Our second P is perception. How do you take data from the world around you and turn it into something that you can act upon? And lots of people are working in perception, right? It's a hugely important field of work for autonomous cars, right? So Waymo, Tesla, all those companies are working on autonomous driving systems, and their perception is hugely important. It's trying to pull in all this data from all the different sensors and combine it into a picture of the world that we can then act on. So in the past, we've done some work on collision avoidance using cameras. We're working on using vision systems to land small drones on ships. And the autonomous soaring work also has a perception component in it, because there we want to be able to detect favorable parts of the atmosphere, share that data among different aircraft, and then be able to exploit all that. And then the other bit that we're working on is cooperation. So how do you get multiple vehicles to work together to achieve some goal, right? And the cooperation side, so the two aspects. One of them is getting several vehicles to cooperatively carry a payload that I mentioned before. It also lives in the autonomous soaring work in the sense of we want to get multiple vehicles to work together to map the atmosphere, and they can share information among themselves and then use that to improve the overall performance of the flock. And we see that happen with turkey vultures as well, right? You rarely see only one turkey vulture in a thermal, because if there's one there, it'll only take a minute or two before it'll be joined by a lot of friends. Right? They all watch each other and see what everyone else is doing. And when a turkey vulture sees another bird in kind of a favorable spot, it will go over and join that bird. So that's why you often see these huge, it's called a kettle of vultures, these huge kettles of hundreds of turkey vultures flying in a thermal together.
So can you explain what sensor fusion is and why it's really important in autonomous vehicles?
Yeah, so sensor fusion is the field of being able to take data from many different sensors. So for example, it could be cameras, a LiDAR, which is like a laser rangefinder, could be sonar systems, GPS is another sensor that we use a lot. And then there's the other sensors that we call the sensors that tell you about what the vehicle itself is doing, right? So that means it's inertial measurement unit. It measures the acceleration of the vehicle, rate gyros that measure the angular rates. And you put all that data together to get a picture of the overall world around the vehicle and what the vehicle is doing within that world. Humans, right? We do all that sort of unconsciously all the time, right? We have our eyes, we have, well, all of our other senses, right? So hearing, smell, right? So kind of in the sense of interacting with the world, right? It'll be mostly eyes and hearing. We have what we call our proprioceptive sensors, which is telling us where are the parts of our body in relation to the rest of our body, right? So if you stick out your arm, right, you know that your arm is stuck out and reaching behind you somewhere, and you know where your hand is in relation to the rest of your body. And then there's the sort of inner ear type sensors that tell you your acceleration as well as your body's angular rates, right? And all that stuff gets fused in your brain to give you a picture of the world around you and how you're placed in that world. And once you have that, you can use that information to figure out what it is you need to do next to get to where you're going. Okay, so all of the sort of robots that operate, right, all have sensors like that in them as well. In the case of airplanes, it'll be things like, well, almost every aircraft has an inertial measurement unit on board, measuring acceleration, angular rates. Many airplanes have, or all airplanes have a compass on board, so you can get a notion of your heading with respect to true north. Most airplanes nowadays have GPS, so you know where you are in the world, right? And then you've got a pilot on board most airplanes that's looking so that you can see what else is going on around you, and then that pilot's controlling the aircraft. In the case of an autonomous aircraft, right, that pilot gets replaced by a little flight controller that either uses, GPS and IMU to navigate, or maybe you would include data from vision systems, right? Computer vision systems to do some stuff in relation to the world around it. And so being able to take all that data and turn it into a big picture, that is this idea of sensor fusion. And there's lots and lots of people that are working on sensor fusion all over the world, and lots of different ways that sensor fusion works, right? Many different ways that people go, and lots of different sort of categories of algorithms that people use to make the sensor fusion work. So a really cool example, right, is to take a look at the videos that a company called Skydio has produced. Skydio makes a little drone that's got cameras all around it, and the Skydio drone is able to take video and follow a person as the person's busy doing its thing, right? A lot of the videos are people doing things like snowboarding or riding mountain bikes. And so the Skydio system is able to avoid collision with obstacles, and it's able to follow the person it's supposed to be following at the same time, right? So, and some of the videos kind of show what the Skydio drone is quote unquote thinking as it's busy flying through the space. It's really neat.
How can multiple different autonomous vehicles use each other's data in order to estimate a value?
Yeah, so that's actually a kind of an example of sensor fusion ultimately, right? So we can have sensors that are on board a single data vehicle, and we put it all together to form a picture of the world. But if I can communicate with sort of other vehicles in my flock and pull in their sensor data as well, now what I'm doing is taking data from sensors that are widely spread apart, right? And that lets me create sort of a more accurate picture of the world for a couple of reasons. One, right? The first one is I can get data from far away, right? Which is cool. The other thing that I can do is I can get data about some object from two different angles of view, and that lets me do things like either I can use information from both different points of view to get information about the shape of the object that I'm looking at. I can also use that to get information about the location of that object in the world, right? So I can triangulate that object's position more accurately if I'm pulling data from multiple vehicles. And really all that happens because I'm getting sensor data from lots and lots of different spots, right? So the more data I can get from kind of spread out places in the world, right, the sort of more information or more accurate information I can then derive about the objects that are in my world.
And what is an autonomous soar flight?
So autonomous soaring is the sort of thing that we try to do where we get a small unmanned aircraft, a little drone, to be able to fly the same way that we see birds like turkey vultures, bald eagles, hawks, golden eagles, fly, and also glider pilots, right? So human glider pilots and hang glider pilots and paraglider pilots. So what all those sort of animals and humans do is they go and look for patches of rising air called a thermal. And then once you fly into that thermal, that patch of rising warm air will carry the vehicle upwards with it. And so what we're trying to do with our little autonomous drones is be able to find these patches of rising warm air, right, and exploit them. Now, it's not just rising warm air we can look for. We can also look for spots where the wind is blowing and gets deflected upwards by things, like, for example, right, the side of a ridge. Here in Pennsylvania, right, central Pennsylvania, where I live, there's the Appalachian Mountains, and there are these long ridges that go, roughly towards the southwest. And when the winds are blowing from the northwest, they sort of hit those ridges at roughly 90 degrees. The winds get deflected upwards. And as a glider pilot, you can fly along in that upward moving air along the ridges. and you can fly enormously long distances at really high speeds along these ridges. In the 1980s, all of the world distance records were being set by glider pods flying out of airports here in central Pennsylvania. Nowadays, the distance records are being set by pods flying along the Andes Mountains in South America. Right, there's a much longer mountain chain that you can exploit there. So the whole thing of autonomous soaring is finding those regions of favorable air motion and then being able to exploit them. And what that does for us is it takes this sort of small vehicle, right, that really has a lot of aerodynamic and physical limitations, right? It's very, very difficult to design a very efficient small aircraft. And those little airplanes are roughly the same size as, you know, all the sort of birds that we see soaring, as those turkey vultures and the bald eagles and the golden eagles are all about the same size. Now, those birds have all evolved these techniques that let them overcome their physical limitations, right, by exploiting atmospheric and favorable atmospheric properties. And so we're taking those same techniques and applying them to these small aircraft using, you know, sort of intelligent guidance and control techniques inspired by what we see these birds do to be able to overcome the physical limitations of the vehicle, right? So we're really trying to use some intelligence to overcome physical limitations.
So what would you say has been your toughest accomplishment so far in your career?
Oh, that's a tough one. Making anything fly is really, really hard. You know, so my students and I, we end up building and flying anything that we work on. We end up building something and flying it. And the time between, you know, the first time we kind of think of a new airplane and we build it, and the time that it actually does the thing that we really wanted it to do, it's probably gone through about 40 or 50 test flights. With small changes happening really every step of the way. And along with those 40 or 50 test flights per vehicle, there's a huge amount of simulation work that we end up doing as well. So the sort of toughest accomplishment is anytime we get a new airplane to actually fly. That's always really, really hard. And the other thing that's really hard is making these airplanes fly reliably, right? So that on sort of any given day, I can tell my grad student, hey, today's a nice day, let's go flying, right? And my grad student can then say, yes, we're ready to go, right? That's also a really hard thing, right? Because the sort of first time you make something fly, you can make it fly once with a few days of notice of working really hard on getting everything working. Being able to fly sort of on any given day with no notice, that's pretty tricky because there's a lot of stuff that you have to make really reliable between there. And then the other thing that's hard is, okay, now I tell my grad student, okay, let's go flying, you know, today. And by the way, I want to fly 10 times today, right? That's also really hard because not only now you've reached the point where, yeah, the vehicle has to work, you know, at any given moment, but now it has to start working over and over and over again at a given moment. So those are really the sort of hardest things that we've been doing so far.
Mm-hmm. And what is a big milestone that you're looking forward to in your research?
So right now, the biggest one is definitely the very first time that Dragonfly is going to be flying on Saturn's moon Titan. And so that is going to, so Dragonfly is supposed to launch in 2027-ish. It is going to spend somewhere between 6 and 8 years on its travel from Earth to Titan, right? So sometime between 2033, 2035, right, Dragonfly is going to fly for the first time on Titan, and that's going to be the absolute highlight milestone of my career.
Mm-hmm. And to high schoolers like me and to younger generations that want to become aerospace engineers, what would your advice be to be successful in this career?
Oh, I'm going to quote Ted Lasso on this one, and my advice is to be curious. I guess I'm not quoting Ted Lasso. I'm quoting Ted Lasso, who's quoting Walt Whitman, right? So be curious. Look at the world around you. Look at basically anything you see and kind of see how it interacts with the world around it, right? So that means look at birds as they're flying. When you see an airplane flying. Take a look at it. Look at airplanes when you see them sitting on the ground, right? Look at the pieces that make up the aircraft. Ask people questions, right? Why is that thing there? How does this particular thing work? What does that do on the aircraft? What do you call that? Right? Those are the things that are going to make you be successful, because that's sort of how you learn the most stuff. And the sort of the big thing is to try and sort of be curious about as many things as you possibly can, because you never know when something that you asked someone a question about a year ago is going to end up being the answer to the problem that you're trying to solve right now, right? And that kind of thing happens all the time, right? That's something that you never thought was going to be important all of a sudden ends up being the answer that you've been looking for. And so that's really the key, right? Is to be curious about the world around you and look at things, and talk to people, right? Because lots of the time people will have the answer or rather, if not the whole answer, then a part of the answer that you're looking for in solving a particular problem. It's the sort of curiosity, I think, that sort of leads us onwards all the time.
All right. Well, thank you for joining me, and thank you for letting me interview you. That was good.
You're welcome. Happy to do it anytime.